Shit, I am live. Okay, am I live on Twitch? Your last stream hit record. Two unique viewers. Shit, two two unique people watched my stream. Myself and someone else. Shit, that is crazy. And am I live on YouTube? Probably am. Just checking it. Shit. Yep, I am live. Okay, so for today, and yeah, these tabs, I was learning how to make a processor from NAND gates, and this is a really good course, NAND to Tetris. Yes, I made registers. I made a bit register, then 8 byte RAM, then RAM 64, RAM 512, till RAM 16, and I was figuring out how to make a program counter which would do these stuff. But now, today, the thing is, I have to do this machine language, modern assembly language. And the last time, where were we? Ah, oh, last time we completed chapter one. Not like the complete chapter one, but a part of it, a huge part of it. We were at around page number 30. And yeah, today we have to complete at least chapter one. Okay, there are examples. Fuck, what the fuck is happening? Where was I? Representing integers. Yes, I did this. Yes, I did this. Yes, I did the examples also. Yep, yep. It was all on his stream. And yeah, yeah, we did that. We did that. Yep, here we are. Memory layout of an execution program. Okay, computer memory consists of number of storage locations or cells, each of which has a unique numeric address. Yeah. Addresses are usually written in hexadecimal. Each storage location can contain a fixed number of binary digits. Each storage location can contain a fixed number of binary digits. Yes. The most common size is 1 byte. The most common size is 1 byte, that is 8 bits. Most computer groups byte Most computers group bytes together into words. Okay, a computer CPU has a that is capable of accessing a single byte of memory is said to have byte addressable memory. Some computers are only capable of accessing memory in word size groups. They are said to have word addressable memory. Okay, so generally the smallest, well, not generally, but literally the smallest unit of data that we can access is a bit. But we do not access single bits, we access them in bytes. Byte is 8 bits. But generally in modern computers, we combine multiple bytes together into a single data format, and we call that a word. And some computers can access individual bytes inside a word, and those computers are said byte addressable, while other CPUs can access data in word words, like the whole word. They cannot access individual bytes, they have to get the whole word, and those computers are called word addressable computers. Now, figure 1.6a shows a section of memory containing some data. Each byte has a unique address that is used when data is transferred to or from that memory cell. Most processors can also move data in word-sized chunks. That makes sense. On a 32-bit system, 4 bytes are grouped together to form a word. That makes sense. 32 bits. The 32 bit, that 1 byte is 8 bits long, and 32 byte would be 4 bits long, 4 bytes long. There are two ways that this grouping can be done. Systems that store the most significant bit of a word in the smallest address. Okay, There are two ways that this grouping can be done. Okay, grouping. Okay, so now we are figuring out how to group different bytes together to store data in as a single word. To store data in word-sized chunks. Okay, systems that store the most significant byte of a word in the smallest address and least significant byte in the largest address are said to be big endian. Okay, the big endian interpretation of a region of memory is shown in figure 1.6b. We have to see it. Viewed as 32-bit big endian little. Okay, this b, this is the diagram. Okay, viewed as bytes. This is the address. This is what is stored at the address. Okay, okay. A, B, C, D, E, F. It goes from below. Okay, A, B, C, D, E, F, and then 0. Okay, and then this is how the addresses are stored. Base 16, base 2. Okay, what is it? Okay, so systems that store. Okay. There are two ways that this grouping can be done. Okay, 4 bytes are grouped together to form a word. 4 bytes are grouped together to form a word. Okay, 4 bytes are grouped together to form a word, right? Because each cell can store a byte. Now we have to store, we have to combine 4 cells to store a 32-bit integer, a 32-bit data, a word that is 32-bit long. So now we have to figure out how to combine 4 bytes so that we can address them as a chunk, as a single storage unit. Okay. So now we have to figure out a system to address those group 4 bytes, because here we are accessing them single byte by byte, but we have to figure out a way so that we can access 4 bytes at a time, right? There are two ways that this grouping can be done. Systems that store the most significant byte of a word in the smallest address and the least significant byte in the largest address are said to be big endian. Okay, that makes sense now. The big endian interpretation of a region of memory is shown in figure 1.6b. Yes, in 1.6b, this is a group of 4 bytes, and if I were to count these numbers, it would be 32. And let's just in case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, shit, 17, 18, 19, 20, 21, 22, 23, 24, 25, 6, 27, 28, 29, 30, 31, 32. Yep. So this is a combination of 4 memory cells, and each memory cell is 1 byte long, and 4 memory cells. So we are calling this group of 4 memory cells a single memory cell. We are treating it as a single memory cell, and we are calling it a 32-bit long memory cell, right? And now we have two ways to store data in it. In these, this big long 4 byte memory cell consists of 4 smaller single byte memory cells, and those single byte of memory cells have addresses, individual addresses, 4 different addresses, and among them there is a smallest address, then one address that comes after it, then the one that comes after it, and then the address that is the largest. And in big endian storage system, big endian, the most significant bit of the number is stored in the smallest address, and the least significant bit is stored in the Largest address. That makes sense. The big Indian interpretation of a region of a memory is shown in figure this one. This. Yep. Uh, these 8 bytes, if they are 8, 1, 2, 3, 4, 5, yay. These 8 bytes are the most significant bits, and this is the smallest address, right? Because after C comes D, D, E, and F, and after F, like we see after F, you get this, you get this. This is the smallest. Okay, that makes sense. Wait, I can see this has to match with this, and that it does. Wait, does it? Yep. 0 triple 1 double 0 1 0, and then this. Yep, that it does. Okay, big Indian. And now is it, why is it called big Indian? Big Indian. End and big. Okay. Let's go move on to the next one. The big Indian interpretation of a region of memory is shown in figure 1.6b. As shown in figure 1.6c, little endian systems store the least significant byte. Little endian system would store the least significant byte in the smallest address and the most significant byte in the largest address. Let's see. System stored the least significant byte in the lowest address and the most significant byte in the highest address. Some processors, such as ARM, which we are using, can be configured as either little endian or big endian. The Linux operating system by default configures the ARM processor to run in little endian mode. Okay, the memory layout for a typical program is shown in figure 1.7. Let's see. This is little endian, so the least, this should be there. Yep, this is here. This is the memory cell with which is the smallest address among the four. One, one, two, three, four, and this is the MSB. This is the LSB, and LSB is stored here in the first address. Makes sense. Figure 1.7. Where the heck is? Okay. Yes, that is good. Stack currently unused. Heap stack grows downward. That is counterintuitive from the physical reality, and heap grows upward. That makes sense. Heap of sand, maybe. Now the program is divided into four major regions or sections. Okay, four major regions or sections. The programmer specifies the context of the text and data sections. The programmer specifies the contents of the text and data sections. The stack and heap segments are defined when the program is loaded for execution. The stack and heap may grow and shrink as the program executes, while the text and data segments are set to fixed size by the compiler, linker, and loader. The text section contains the executable instructions, while data section contains constants and statically allocated variables. The size of text and data segments depend on how large the program is and how much static data storage has been declared by the programmer. The heap contains variables that are allocated dynamically, and the stack is used to store and the heap contains variables that are allocated dynamically. Okay, the heap contains the variables that are allocated dynamically, and stack is used to store parameters for function calls, return addresses, and local automatic variables. Okay, okay, right. So first we have text and data. Stack is above, and is a typical memory layout for a program with 832-bit address space. And I am supposing that this thing represents the physical memory, not the virtual memory through which a program accesses the physical memory. So I am supposing this is representation of the physical memory, because we have some stuff going on over here and some stuff going on down here. So that makes sense, because if this were the virtual memory, then I would get the whole memory to myself, but I'm not getting the whole memory for my program. I am seeing some crazy stuff up here and some crazy stuff down there. So this seems to be the physical memory, and uh, in that physical memory, I get a little chunk of that memory to myself for the execution of my program, and that chunk is organized as such. Stack. I got stack here. Then I got currently use unused thing. Yeah. Okay. It is the space for the stack and the heap to grow into. Then we got data and text. Text is stores the instructions. This is the data, the operands on which the instruction is supposed to happen, and stack and heap contain their own stuff. Stack contains things that need order, like recursive calls, call stack in JavaScript, and that closures, closure data shit. Yes, but there's something that I don't get here. Does every program get its own stack and heap? Because this makes it seem so. Let's see. Uh, the Shanava does gets its own. Well, they do get their own uh, data and text section, but we have to see if they get the, because they certainly do get their own data and text section, chat sections in the memory. Or it could be that they get their own stack and heap in the virtual memory, which is mapped onto a single big stack and heap onto the physical memory. Let's see. Yes, every program gets its own stack and heap during execution. Ah, shit. So how does it? How would it work? Because I know that the stack pointer SP is stored in the register, but there is a single register for the stack pointer. How does that work? All right. Is the stream fucking lagging? I have one viewer, that is me. Yeah, I'm watching myself, and I have something going on here. I suppose there is no super chat. Shit, it is lagging here also. Shit, something. Or it could be that they get their own. Okay, stop the volume. I do not want to listen. Neither do you guys, if anyone is there. No followers. Shit. Okay. Yes, every program gets its own stack and heap during execution. In addition to its data and text sections, here is an example of how memory is typically organized for each program. Memory layout of a program. When a program is loaded into memory, its process is given a virtual memory. This space is typically divided into following segments. Text segments contain the instruction, contains the program's compiled code. instructions shared among processes if the program is executed multiple times to save memory. Read only to prevent accidental modifications. Data segment holds global and static variables, holds global and static variables like int a equals to 420, subdivided into data segment. Initialized data segment stores variables with explicit initial values. Uninitialized data segments, BSS, that is not the full form, uh, stores uninitialized variables defaulting to zero. Oh yeah, zero string, I guess. Heap, used for dynamically allocated memory. Used for dynamically allocated memory, like malloc, calloc. Fuck. Oh, it is called a new in C++. That is Pythonic, using malloc in C or new in C++, managed explicitly by the program through allocation and deallocation. Oh yeah, and okay, okay, and if I do not free dealloc the memory, then I get errors that the memory is fixed, that the memory is taken, completely gone. Grows upwards towards higher memory address. That is what they mean by upwards, not like the fucking orientation. Uh, they mean ascending order. Stack, used for storing local variables, function arguments, return addresses, and call frames. Grows downwards toward lower memory addresses, managed automatically through function calls and returns. So if I am inside a function and I call another function, then the new function call will be added on top of the stack, which is like it grows downward, so the orientation is flipped. But think about it like this: the new function is added on top, and if I call another function from that inner function, then that function will be added on top of that. And when I'm finished executing this other function, it will be it will pop out from the stack, and the pointer will be here on the inner function that I first called. And then when it is done executing, it will pop out of the stack, and then I will be pointing on the last original function that I was working on. And then when it is popped out, then we have maybe something else, the main program, maybe the program ends. Other segments, okay. So difference between heap and stack. Heap contains objects, data. It contains data which is stored dynamically. It has this data which is stored in the storage which was demanded from the computer during the execution of the program. It is used to store the variables and data that were demanded during the execution of the program. And stack stores data that requires an order, right? Like recursive calls one after another, and call stack and stuff like that. Other segments: memory mapped segment for shared libraries, reserved space for kernel. Kernel is good. Kernel memory or system reserved area. Stack and heap in separated programs. Okay. Each program or process running on an operating system gets its own virtual memory space, which includes a separate stack and heap. Here is why. Isolation. The operating system provides each program with a private virtual memory space to ensure isolation. Programs cannot interfere with each other's memory. Okay, with each other's memory, text, data, stack, or heap. Okay, stack. Each process has its own stack, which grows and shrinks with function calls and returns. And if you call a lot of functions, then the stack gets really big, and it can hit the heap that is below it, and You get stack overflow. The stack is typically small and has a fixed size allocated to at the start of the program. Fixed size allocated at the start of the program. Okay, because you cannot have an infinite sized stack because there are other programs and you have limited memory. Share and care, baby. Heap. Okay, each process has its own heap for dynamic memory allocations. Hmm. The heap grows and shrinks as the program allocates and frees memory. Multiple programs running simultaneously. While the memory layout is conceptually the same for all programs, the virtual memory abstraction allows each program to think it owns the entire memory space. Vanity. The operating system's kernel maps each program's virtual memory to the actual physical memory key points, text and data segments shared if the same program is executed multiple times but isolated per process in terms of modification. Shared if the same program is executed multiple times but isolated per process in terms of modification. If same program is running multiple times, then it will be mapped onto the same physical place. But if the program is making modifications to its own code, then those modifications made by a single program will not show onto the uh, uh, same program that is used by another program. uh, okay, they are the same unless they are not always private for each program process to ensure correct operation and isolation. Threads that I don't get, mm, because I have not studied threads. If a program has multiple threads, each thread has its own stack but all threads share the same heap. Let me know if you want to go deeper. Okay, yes. Okay. So each program has its own stack, but there is also a stack pointer in the register. CPU register is that stack pointer for the kernel itself. Is that the stack pointer which the kernel uses? The CPU itself has a stack pointer register, which is only single, not married, which is single. You are saying that each program gets its own stack, but there is only a single stack pointer. So, how does that work? Or is the stack pointer in the CPU register used only by the kernel itself to keep track of its own processes? Let's see. Yes, you are correct. Great question, Sheikh. You are correct that the CPU has a single stack pointer register SP, and you are also correct that every program gets its own stack. This apparent contradiction is resolved by understanding how modern operating systems and CPUs manage processes. Okay, modern how the stack pointer works with multiple stacks. Mm. Ah, The stack pointer register in the CPU always points to a current top of the stack. Yes, for currently executing process or thread. However, the way multiple stacks are managed the way multiple stacks are managed boils down to context switching and how the operating system manages memory for each process. Okay, the stack pointer SP register in the CPU always points to the current top of the stack for the currently executing process or thread. Always points to the top of the stack for the currently executing process or thread. That makes sense. However, the way multiple stacks are managed boils down to the context switching and how the operating system manages memory for each process. Okay, context switching is something. Key concepts: per process memory isolation. Each process gets its own virtual memory space which includes its own stack. When the operating system schedules a process to run on the CPU, the stack pointer SP is set to when the operating system schedules a process to run on the CPU, the stack pointer register SP is set to point to that process's stack in its memory. When the operating system schedules a process to run on the CPU, the stack pointer register SP is set to point to that process's stack in its memory space. Okay, okay. The stack pointer points to the top of the current stack, but the stack itself changes with each process. It always points to the top, but the stack on whose top it is pointing to changes with each process. Hey, context switching. The operating system uses a mechanism called context switching, which I'll be implementing when I will be making my own operating system in Rust. I don't know Rust and I do not know how to make an operating system, but time teaches. Called context switching to handle multiple processes. Okay. During a context switch, the operating system saves the current process's CPU state, including the stack pointer, seems like stash in Git, loads the CPU state, including stack pointer of the next process to run. That is a lot like stash in Git. Stack pointer for threads. Shit, I do not know threads. I have no experience with threads. Each thread within a process also gets its own stack. During a context switch between threads, the stack pointer is updated to point to the stack of the currently executing thread. How the kernel uses the stack pointer. The kernel also gets its own stacks. Stacks, shit, multiple. Separate from user processes. Here's how it works. Kernel stack. Every process typically has a small kernel stack in addition to its user space stack. The kernel stack is used when the process transitions from user mode to kernel mode. Example, during a syscall or interrupt. The CPU stack pointer switches to point to the kernel stack during these transitions. The CPU stack pointer switches to point to the kernel stack during these transitions. Okay, they are like okay, so the a process when it uh, wants the kernel to do something by syscall, it calls the kernel and it calls the kernel. It uses the kernel API to make system calls to tell the kernel what it wants the kernel to do, and during that time the kernel comes into effect and the stack pointer points to the switches to the stack that is being used by the kernel for that process. Okay, the CPU stack pointer switches to point to the kernel stack during these transitions. System-wide management. The kernel uses the stack pointer register during its own execution, but this does not interfere with the user processes because the CPU saves and stores the stack pointer during context switches. That is pretty interesting. When the CPU switches, context switching is a thing. When CPU does, when the operating system does the context switching, then uh, the state of the CPU, the values in the register, and the address of the stack pointer is stored somewhere in the memory magically, and then the state that is that should be used for the execution of this new program is brought into the CPU. Everything is updated, the registers, the general purpose registers, and the stack pointer is updated. And this new program is runs. The new program runs. Shit. Why the stack pointer isn't a limitation? The stack pointer is a per CPU register, but actual memory it points to depends on the current process context. When a new process is or thread is scheduled, the OS updates the stack pointer SPE to point to the stack of the active process or thread. Each process's stack is stored in its virtual memory, so the stack pointer simply needs to point to the current location, to the correct location. A stack pointer SP always points to the current process or thread's stack. Each process thread has its own stack memory managed by the OS. During a context switch, the OS saves the current stack pointer and loads the stack pointer for the next program or thread. The kernel also has its own stacks, multiple, each stack for every process that needs the kernel. I think every process needs the kernel. Of course, it needs the kernel. If the process is running, it maybe it will show something on the screen for which it has to access the screen, the screen, computer physical screen, and for that it has to make a syscall. Let me know if you'd like an illustration or further details on how this is done. Okay, I do get this part now, but I'm stupid and I need to announce that I'm streaming. Shit. Okay. Yes, only 36 minutes. I thought an eternity has passed. What do I do? World statics. What comes to mind when you think of Narendra Modi, Prime Minister? Uh, Live. Yo. No. Yo. Me. Uh, Me. Live. E, uh, 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 join. Join. Me. Okay, and at a time I can only type in one link in here. That is what I um, discovered the last time I was tweeting something. So where do I get the link for this thing? Bitrate is unstable. Why? Poor connection detected. What the heck is wrong? I'm on 5G and is the video buffering? Use the low latency toggle under the advanced system settings. Okay, advanced low latency toggle is already on. I will have to figure something out for this, for low bit rate. Twitch TV, the link for my channel, Walrus, Force a Walrus. I can send two links at the same time. Maybe I cannot. Okay, I get Twitch TV here and YouTube here. That is also good. Yep, I got gained a subscriber. That is 39. One watching. It is me. Shit, I'm watching myself and my stream is lagging. I will definitely have to figure something out. This is not working out. I have to make the stream low latency. You guys won't watch it like you are watching it in the first place. But yeah, in a high level language, storage space for a variable can be allocated in one of the three ways. statically, dynamically, and automatically. Statically, okay. Statically allocated variables are allocated in the dot data section. Dot data section in the assembly language. The storage space is reserved and usually initialized when the program is loaded and begins execution. Okay, those are statically typed variables. The address of a statically allocated variable is fixed at the time of the compilation. The program begins running. Yes, yes, of course, not at the time of the compilation, because if it were, uh, if the memory for a program were to be uh, were to be allocated for it during its compilation for a static variables, then only compiling a program and not executing it would take up memory. And if you were to compile a program again and again and again and again into different executable files, then it will fill up your memory, which is very stupid. Okay, so statically allocated variables, the addresses for these are fixed at the time when the program starts running, begins running, and cannot be changed. Automatically allocated variables, often referred to as local variables, are stored on the stack. Okay, the stack pointer is adjusted down to make space for newly allocated variable. Okay, like user input, the address of an uh, automatic variable is always computed as an offset from the stack pointer. Okay. Dynamic variables are allocated from the heap using malloc new or a language dependent equivalent. The address of a dynamic variable is always stored in another variable known as a pointer. The address of a dynamic variable is also always stored in another variable called a pointer, which contains the address for that for the value of that variable, which may be an automatic or a static variable. The pointer itself can be a static variable. Oh, okay. I can uh, define a variable which will store pointer, which points to something in the heap, right? And it will store the address when I actually malloc the space, and the space which I malloc will be given to me during the execution of the program. uh, but the pointer itself, the uh, the pointer itself, which lives in the data space of the program, will get its own address and a space and the when the program begins. The address of a dynamic variable is always stored in another variable known as a pointer, which may be automatic or a static variable or even another dynamic variable. The four major sections of a program memory correspond to executable code, executable code, statically allocated variables, dynamically allocated variables, and automatically allocated variables. Right. Executable code, the code itself, the binary code. Statically allocated variables, int a equals something. Dynamically allocated variables, malloc, which is given to me these the values, the data for these lives in the data section here. And no, no, oh, shit, I'm stupid. And the data for these statically allocated variables lives here in the data section. The data for dynamically allocated variables lives in the heap, and for automatically allocated variables, it lives in the stack. Okay. Now, chapter summary, and then oh shit, fuck, 13 exercises, and that should be enough for today. There are several reasons for computer scientists and computer engineers to learn at least one assembly language. AArch64, there are programming tasks that can only be performed using assembly language, and some tasks can be written to run much more efficiently and or quickly if written in assembly language. Programmers with assembly language experience tend to write better code even when using a high level language, and usually better at finding and fixing bugs. Although it is possible to construct a computer capable of performing arithmetic in any base, it is much cheaper to build one that works in base 2. It is relatively easy to build an electrical circuit with two states on off hello using two discrete voltage levels, but much more difficult to build a state stable circuit with 10 discrete voltage levels. Therefore, because the error level is high, therefore modern computers work in base 2. Computer data can be viewed as simple bit strings. The programmer is responsible for supplying interpretations to give meaning to those bit strings. A set of bits can be interpreted as a number, a character, or anything that the programmer chooses. There are standard methods for encoding and interpreting characters and numbers. ASCII, the first one. Then we have Unicode. Now shows some common methods for encoding integers. The most common encodings for characters are UTF-8 and Unicode and ASCII. Computer memory can be viewed as a sequence of bytes. Each byte has a unique address. A running program has four regions of memory: stack, heap, data, text. One region holds the executable code, text. The other three regions hold different types of variables. Now, the exercises. Shit. Uh, yep. Close ChatGPT for the exercise. What is 2's complement for this? That is pretty easy. Just sheet. This number I want to find. So just flip the bits and then add one, which is simply this. So this is the answer. Easy. Okay. Then second, perform the base conversion to fill in the blank spaces in the following table. This is tedious and pretty easy. Okay, let me do this mentally. 23. It would be there would be 1 for 6. Okay. 23. Let me do it orally. 1 for 16. After subtracting 16, I get 4, 7. So 0 for 8 because I get 7. So 1. 1, 0, 1 because I need 4. Then I need 3. And yes, 1, 1. So the answer is 1, 0, 1, 1, 1 for 23. And it is like too stupid to even check this. Um, it would be really funny if this is wrong. 1, 0, 1, 1, 1 should be 23 and 23. Okay, now this into base 10 into base 16, it would be 1 no f for 16. Then I have 7 remaining. F7. F7, I've heard that before. F7. F7. 23. No, 1. Ah, what's that? F is like full. No, I don't need full. Okay, for base 21, and I have 23. 1, 1 to 12 seems good. Shit. Custom base? Text. What is text base? Okay. What is this in base 10? This is 3 plus 4, 8. 3 plus 6, 19. This too easy. Okay. What is the 8-bit ASCII binary representation for the following? I guess for capital A, it is 56. And yeah, the representation for capital A is smaller than the representation for smaller a. For small a, I guess it is 97, and for capital A, it is 50 something. I have to check. Uh, Lawsuit is there. Yes, ASCII table. Well, that is absolutely beautifully visible. Shit. Yes, this is. Okay, and why the fuck is it SVG? Okay, that was wrong. I said 57. This is 65 and small a 97. That is correct. 97 and 65. I don't need to remember that, but okay, cool trivia. And something about this. What is this minus this? Given that this and this are ASCII characters, give your answer in binary. Why are they asking trivia questions? Okay, ask. I do not have to remember the ASCII table. It is like, okay, Wikipedia, but like I have to figure out the answer. So yeah, this is 33. This what was the other character? Slash slash this 92. 92 minus 33. Why wasn't it 32? Shit. 59. Yep, seems like 59 and 59. Yeah, 92 minus 33. That is 92 minus 32, which is 60 minus 1, 59. 59 in binary is 1 for 32. Then I would need 1 for 16. 48. Get. Then 1 for 8. And 48, 56. Then I need 3, then 0, 1, 1. That is 1, 1, 1, 0, 1, 1, 1. 1, 1, 1, 0, 1, 1, 1. That is the answer for this. Give your answer in binary. I gave you my answer in binary. Representing characters. I don't have any way to check, and I don't even want to check for these simple questions. Representing characters. Convert the string super to its ASCII representation. So yeah, show your result as a sequence of hexadecimal values. No, no, that is just tedious slave labor. Convert the hexadecimal sequence into a sequence of values in base 4. Still slave labor. Suppose that the string "this is a nice day" is stored beginning at the address this. Okay, what are the contents at address this in hexadecimal? That is good. Okay, so 9 A C and B1 AC. From AC to B1. If AC is the starting, if AC is the starting, eh, wait, what? What? Ah, not working. Shit. Chrome is not working. Ah, yep. We had AC and we had to go. We had to go to B1. From AC, you have AB, AD, AE, ABC, D, E, F, then B1. Okay, and okay. Ah, what is the string? The string is this is a nice day. Uh, so THIS, then space is stored at this address in hexadecimal. What is hexadecimal for a space? I will have to look up in the ASCII table, and it turns out that space is 32, and we also have a 94 character, which is just, oh, it is what do you call it? This is not tilde. What is this? What is the, how do I find out its name if I do not know how to refer to it? What is the name of this? Well, depends on the type and meaning. Plus minus. Oh, Google is not unable to see the symbol. What is sheet? It is called. Just give me the answer. This symbol is called caret. Carrot top. Yes, carrot. Okay. Perform the following conversions. That is what they make us do in college, and this is slave work. Okay, given the following string, that looks really cool, and I would like to do it, but it is slave work, not very smart. This is what they mean when they say don't work hard, work smart. This is what they mean, right? I know how to convert these, right? Convert it to hexadecimal, convert the first 4 bits to a string of base 10. Convert the little endian half word to base 10. What is that? Little endian, which means the smallest address, which we will suppose this is the smallest address, contains the least significant bit, right? And we will suppose that this is a 32-bit system, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 into 2, 16, 16, 1, 2, 3, 4, 20 bytes. And if this is a 32-bit system, then 4 bytes make one word, and therefore we have 5 words, and half word would be the half of the first word, which will contain these 2 bytes, and convert the half word to base 10. So which half? The most significant half or the least significant half? Well, I guess discussing this much about it shows that I know this. Okay, if this string of byte were sent to an ASCII printer, what would be printed? Find the symbols that these values represent and print them. The number this is stored in a 32-bit word starting at address. This shows the address and contents of each byte of the 32-bit register. What is the largest value that 8 bytes can store? 255. So this will not suffice itself in 255. And in little endian system, the least significant bit will come in the first registers, and there are first memory cell, and each memory cell is 1 byte long, and we have 4 of them because this is a 32-bit word, right? In the little endian system, the least significant bit will come in the first memory cell, and by first I mean the memory cell with the lowest memory address. Starting from this, big endian will have the most significant bit in the lowest address. The ISO, International Standard Organization, IEC, 10646 standard defines 1 112 064 code points, glyphs, characters, symbols, things. Each code point could be encoded using 24 bits or 3 bytes. The UTF-8 uses up to 4 bytes, that is 32-bit, to encode a code point. Give 3 reasons why UTF-8 is preferred over a simple 3 byte per code point. It can uh, contain much more symbols. It increases the range of the symbols that we can use, and for and it if the system is 32-bit, which generally systems are 32-bit and 64-bit. So if the system is 32-bit, then it each glyph will take half word, and if the system is 64-bit, then it equals 1/4 of a word, which is like very beautiful definition. And if we were to use 24 bits, then it would be like uh um, 3/4. No, if it is 32 bit, then 32 bit are required, and it is equal to a word in a 32-bit integer, but equal to half a word in a 64-bit system. UTF-8 is often referred to as Unicode. Why is this not correct? Unicode is the foundation. UTF-8 is a product of the foundation. That is what I think. Between resistance, temperature diagram, and so U and UTF-8. UTF Unicode is a standard that assigns a unique code point to each character across different languages, while UTF-8 is a specific encoding method that translates Unicode code points into a sequence of bytes to store to be stored digitally. That does not clear things. Unicode, a character set that assigns a unique numerical code to each character. That is a dictionary key value pair, doesn't specify how to store these codes in a computer. Okay. Unicode is a mapping of characters and bits which represent that character, used to represent characters from various languages, including symbols and goddamn emojis. UTF-8, a specific encoding format for Unicode characters, uses a variable length byte system, meaning some characters may take up 1 byte while others might require more. Widely used to its efficient storage and common characters. Okay, okay. So Unicode is a mapping between sequences of zeros and ones to symbols like C, like a C. Yeah, it has a specific sequence of zeros and ones which represents a C. Well, you have a choice. You can either store that whole sequence in your text file, which will represent a C at that specific position. Or you can use an encoding format which reduces the storage that it takes to store those mappings. So UTF-8 is like a compression program, uh, not a compression program, but an algorithm, more like, right? And Unicode is a mapping. Yes, there is a difference. Skilled assembly programmers can convert small numbers between binary, hexadecimal, and in their heads. Headless, without referring to any tables or using a calculator or principal in the blanks in the following table. Well, this is a ego thing now. So 5 is 1 0 1. 5 is 101, and hexadecimal is 5 1011. 6 6 6 C, 10 11 12. C is 12, right? 12. How you define 12? 12 is 8 1. Shit, head in my head. 12 into binary. 148. Oh, 110 0. How many zeros? 3 zeros. 141, 142, 144. Oh, no, 0 for 4. 8 and 4. I want 8 and 4. 8 and 4. And then 0 for 2. 0 for 1. It's like, wait, 1, 2. Oh, did I skip this? 5 was 111. And this is 2 plus 4. 2 plus. I am stupid. This is 10. 10 and A. Okay. C 12 1 1 0 0. And 23 we did above. 23 was 1 and wait, 23 12. Fuck, 1 7 17 17 in hexadecimal, and in binary 23 was 1 16, then 0 0 and 1 1 1. Yes. And then we have this behemoth 1 plus 4 plus 8 13 plus 13 plus 32 45. So 45 in decimal and 45 in hexadecimal would be fuck. Mm-hmm. 15. Wait, what was the number? 40. 5 45. So 45 here, and this becomes 45. Huh, is it like 30? Shit, seems correct. Hexadecimal to binary, 30. Shit, this has to be correct. But has to be 45. 30 is 48. Okay, why is it 48? 16 16 16. Stupid. Okay, so 20 and F minus 1. This is embarrassing. Okay, I get 32 with 2 at 16th position. 16 into 2 32. And then what do I have to get? I have to get 13. What is 13? 13 is D. 45. Shit. And then we have 4b, 4 into 16, 64. 64 plus b is 11. 64 plus 11, 75. And so that is 75 in decimal, and in binary we get 64 minus 75. Oh, we can directly convert it into from hexadecimal to binary. 4640. For four is like 100 in binary, and then but I have to use like how many spaces? 8 to represent a no 4. I have to use 4 spaces, 4 places to represent this 4. Is 0 1 0 0 0 1 0 0. Okay. Let's see. No, uh, binary to hexadecimal. So I'm saying it should be 0 1 0 0, and then b is 12. 12 is 12. 12 is take 8 1 0 0. Shit, this should be 4b. That is 4c. B is 11. 12 is c. Yes, 11 is shit, I'm very c. How? How? Right. What are the differences between a CPU register and a memory location? Well, CPU register is a storage thing, is a memory cell, is a place where you can store data. It is located inside your CPU, inside the processor itself, like the Intel chip or M1 chip. It is stored inside the processor, while memory is the RAM, which is removable. You can remove the RAM and insert it, and the CPU can access data from the RAM. There's a difference. This page intentionally left blank. Keep that in mind. That might come in the exams. GNU assembly language. How long is this? 36 to 50. And what is there? Labels, comments, directives, assembly instructions, structure of an assembly program. Interesting. What the assembler does. GNU assembly directives. GNU assembly directives. GNU assembly syntax. Selecting the current section, allocating variables and constants. How long have I been streaming? Like, not very long. Shit. Prime Minister was just here. He just left. Wait, there are two people watching my stream. Okay. Uh, uh, that is lagging. Shit. Embarrassing. Huh, is it? Shit, I lost a subscriber. It was 10 before when I last came here. It is lagging really hard right now. I actually have to figure something out. 73 minutes. I have been streaming for 73 minutes. Charge. Charge. Uh, One viewer, that is me. Truly. And maybe if I turn this off. But for this stream, I am using my downstream data, and for the OBS I'm using upstream. So these should not be interfering with each other, right? Next, assembly. Okay, let's complete this section at least. A structure of an assembly language. Okay, let's read about the structure of an. All modern computers consist of three main components: the central processing unit, and my mouse is stuck. The central processing unit, CPU. Yo, it, it is still stuck. Oh, I have to get a better setup. But that takes time. Okay. All modern computers consist of three main components: the central processing unit, CPU, memory, and devices. It can be argued that the major factor that distinguishes one computer from another is the CPU architecture. The architecture determines the set of instructions that can be performed by the CPU. The human readable language, which is closest to the CPU, is the assembly language. Architecture is assembly language. When a new processor architecture is developed, its creators also define an assembly language for the new instruction, for the new architecture. In most cases, a precise assembly language syntax is defined as, and an assembler is created by the processor developers. Because of this, there is no single syntax for assembly language, although most assembly languages are similar in many ways and have certain elements in common. The GNU assembler, GAS, is a highly portable, reconfigurable assembler. Okay, GNU assembler, GA. Oh, G for GNU and A is for assembler. GAS uses a simple general syntax that works for a wide variety of architectures, although the syntax used by GAS for the RAM, for the ARM processor, is slightly different from the syntax defined by the developers of the ARM processor. It provides the same. Oh, copyright. Shit. Is slightly different from the syntax defined by the developers of the ARM processor. It provides the same capabilities. Mhm. Structure of an assembly language. An assembly program consists of four basic elements: assembler directive, label, assembly instructions, and comments. Comments I get assembly instructions. Okay. What are labels and directives? Assembler directives allow the programmer to reserve memory for the storage of variables, control which program section is being used, define control which program section is being used, define macros, include other files, and perform other operations that control the conversion of assembly instructions into machine code. The assembly instructions are given a mnemonics. I know the meaning of this word, but I cannot read it. Mnemonics are short character strings that are easier for human brains to remember than sequences of binary, octal, or hexadecimal digits. Each assembly instruction may have an optional label, and most assembly instructions require the programmer to specify one or more operands. Most assembly instructions, okay, each may have an optional label. Okay. Most assembly language programs are written in lines of 80 characters. Lines of 80 characters. Each line cannot be larger than 80 characters. Organized in four columns. The first column is for optional labels, like these. In the first column is for optional labels. The second column is for assembly instruction or assembler directives. The third column is for specifying operands, and the fourth column is for comments. Traditionally, the first two columns are 8 character wide. The third column is 16 character wide, the one for the instruction. Then the last column is 48 character wide. First 8. Then the first two columns are 8 characteroids. Oh, oh. First for this, the label. Then for assembly instruction itself takes 8 character, can take 8 character. Then the operands can take uh, 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 can take can take 16 characters, then 48 for the comments. However, most modern assemblers, including gas, do not require a fixed column width. Listing 2.1 shows a basic Hello World program written in GNU ARM assembly to run under Linux. For comparison, listing shows an equivalent program written in C. The assembly language version of the program is significantly longer than the C version and will only work on an ARM processor. The C version is at a higher level of abstraction and can be compiled to run on any system that has a C compiler. The C is referred to as a high level language and assembly is a low level language. Assembly code, C code. Gotcha. Labels. Most modern assemblers are called two pass assemblers because they read the input file twice. On the first pass, the assembler keeps track of the location of each piece of data and each instruction and assigns an address or numerical value to each label and symbol in the input file. The main goal of the first pass is to build a symbol table which maps each label or symbol to a numerical value because they read file the input file twice. Okay. On the first pass, the assembler keeps track of the location of each piece of data and each instruction and assigns an address or numerical value to each label and symbol in the input file. The main goal of the first pass is to build a symbol table which maps each label or symbol to a numerical value. On the second pass, the assembler converts the assembly instructions and data declarations into binary using the symbol table to support numerical values whenever they are needed. In listing 2.1, there are two labels, main and stir. Okay, during assembly, those labels are assigned the value of the address counter at the point where they appear. During assembly, those labels are assigned the value of the ad. Those labels are assigned the values of the address counter. Address. I guess I will understand them as time goes and I do more things. Labels can be used anywhere in the program to refer to the address of data. To refer, labels can be used anywhere in the program to refer to the address of data. To refer to the address of data, functions or blocks of code in GNU assembly syntax, labels always end with a colon character. During assembly, there are two labels, main and stir. During assembly, those labels are assigned the value of address counter at the point where they appear. This and this is a label. They store the address for this thing, and this stores the address for this thing. Comments. There are two basic comment styles, multi-line and single line. Multi-line comments start with this slash and star, and everything is ignored until a matching sequence of star dash is found. Though these comments are exactly the same as multi-line comments in C and C++, in ARM assembly, single line comments begin with a character, okay, somehow, and all remaining characters on the line are ignored. Listing 2.1 shows both types of comment. In addition, if the name of the file ends In .s, then the single line comments can begin with double slash. If the file name does not end in capital S, then the double slash syntax does not work. Okay, two ways to add comments: multi-line and single line directives. Directives are used mainly to define symbols. To define symbols, allocate storage from the memory, and control the behavior of the assembler, allowing the program to control how the assembler does its job. The GNU assembler has many directives, but assembly programmers typically need to know only a few of them. All assembly directives begin with the dot period, which is followed by a sequence of letters, usually in lowercase. Listing 2.1 uses the dot data, dot askeys, dot text, and dot global directives. The most commonly used directives are discussed later in this chapter. There are other directives available in the GNU assembler which are not covered here. Complete documentation is available online as part of the GNU bin utils, binary utils package. Assembly instruction, the instructions themselves. Assembly instructions are the program statement that will be executed on the CPU. Most instructions cause the CPU to perform low-level operations. In most assembly languages, operations can be divided into few major types. Some instructions move data from one location to another. Others perform addition, subtraction, and other computational operations. Another class of instructions is used to perform comparisons and control. Which part of the program is to be executed. Next, chapter 3 and 4 explain most of the assembly instructions that are available in ARM processor. The next chapter and the one after it. Now that part is done. What the assembler does, we can do that. We got this. Listings 2.3. Shit. This. Okay. Shows how the GNU assembler will assemble the Hello World program from listing 1. Okay. The assembler converts the strings. Oh, oh. The assembler converts the strings on input line 2 into binary representations of the string. The results are stored in hexadecimal in the code column of the listing. The first byte of the string is stored at address 0. The first byte, most significant byte, is stored at the first address, supposing that it is the smallest is in its value. Then this means it is in big endings big endings section of the program, as shown by the 001 in the adder column in line 2. So this gets converted into this, which makes sense, and this gets converted into this this and this. Shit. Text and dot global is whatever. This, then this whole thing is converted into this. That is crazy. This instruction means this and this. No, this represents this, I guess. There, there's a mapping. Okay, page 2. Monkey brain trying to understand assembly language. On line 4, the assembler switches to the .text section of the program and begins converting instructions into binary. The first instruction on line 9 is converted into 4-byte machine code this and stored in location this in the .text section of the program as shown in the code and address column in line 6. Oh, this is the address, this is the code. Address code, address code, address code, address code, address code. First, this store, this is store, and the addresses are going up by 4, which means 32-bit processor. baby. Okay. Next, the assembler converts the LDR instruction on line 10 into the 4-byte machine instruction this and stores it at address this. It represents this process with each remaining instruction until the end of program. The assembler writes the resulting data into a specially formatted file called an object file. Note that the assembler was unable to locate the printf function. The linker will take care of that. The object file created by the assembler hello.o contains the data of the code listings. Listing 2.3. Sorry, my bad, kill me. Along with information to help the linker to link or patch the instruction on line 11 so the printf is called correctly. For this, go here. For this, go here. Printf. After creating the object file, the next step in creating an executable program would be to invoke the linker and request link that it link this with the C standard library. The linker will generate the final executable file. First converted into object, then different objects are connected. Objectifying. Containing the code assembled from hello.s along with the printf function and other standard code from the C library. The GNU C compiler is capable of automatically invoking the assembler for files that end in .s or .s and can be used to invoke the linker. For example, if listing 2.1 is stored in the file name hello.s in the current directory, then the command gcc is GNU C compiler. That is crazy trivia problem. Then the command this will run. Shit. Will run the GNU C compiler, telling it to create an executable program file named hello. And to use with hello file will contain zeros and ones only and nothing else. To use hello.s as the source file for the program. And output should be this, and this is the file that you need to assemble. The C compiler will notice the .s extension and invoke the assembler to create an object file which is stored in a temporary file, possibly named hello.o. Then the C compiler will invoke the linker to link the hello.c with the C standard library, which invokes the printf function and some startup code which calls the main function. The linker will create an executable file named hello. When the linker has finished, the C compiler will remove the temporary object file. This first creates an object file and it sees that it ends in .s. Therefore, it creates it calls the linker function, which links the hello.o, which is an object file, with the things that object file requires and forms a binary executable file which is called hello, and then deletes the .o object file. Shawshank Redemption. Okay. GNU directives. Okay, tomorrow we will complete this chapter. How long has it been? It's been 1 hour and 34 minutes. Has it been long enough? No, I can stream more. Well, the stream seems to be going properly now, and my camera is not good. Mostly I'm here. Shit, that should not happen. Should be somewhere here, but then I go closer to the screen. See, shit, I have to be here, right here, and I'm using my phone as a camera. That is why I'm looking unhandsome. Uh, hmm, that seems okay. Today we completed the remaining part of the first chapter and two sections in chapter 2. Then tomorrow we will at least complete chapter this second chapter, and then from day after tomorrow, should day after tomorrow would be difficult to stream. I will not be streaming this because I have my exam. So I will be streaming something else. And let's see the index. Beautiful index. Okay, gonna go some bleach index tomorrow. This will be completed. Then we will get on with chapter 3, which tells us about instructions. ARM64 is this is the ARM64 bit language, right? Modern assembly language is ARM processor. I am fucking stupid. This is not the book that I am supposed to be reading. Just fucking hell. And you did not saw that programming with languages, and is this is the one. That is funny. This is the one. Modern assembly language. Don't delete this one and put this one here. Close that one. So, is there any difference? Like most of the stuff that we read uh, has to be same. Most of the stuff that we read has to be same. And now let's see. Here we started from here, and then the examples that it gives is for a 32-bit ending register, still 32-bit. That is what we read. And heap stack currently used, heap unutilized data.bss, read only data, initial program code dot text dot data dot road. Shit. Okay, so there are some differences. Okay, I would suppose that this would not be a lot different. Okay, the code is different, but the definitions are the same. What the assembler does, it assembles. Okay, so a thing that is different is this. In a high level language, the memory layout for a typical program, as shown in figure 1.7, the program is divided into 6 major memory regions. The last one said that it has 4, which was an older book. Or maybe this one is going into more detail and considering the subdivisions of I think as their own thing, as their own sections. The programmer specifies the contents of the .text, .data, .read only data, and .bss sections. The stack and heap sections are defined when the program is loaded and executed. The stack and heap may grow and shrink as the program executes, while the other sections are set to fixed sizes by the compiler, linker, and loader. The .text section contains the executable instructions, the .data and .read only data, and .bss. Okay, so last one, I guess considered these three as one section. Sections contain constants and static variables. The size of .text, .data, .read only data, .bss. Sections depend on how large the program is and how much static data storage has been declared by the programmer. The heap contains variables that are allocated dynamically. The that are allocated and dynamically, and the stack is used to store parameters for function return addresses and local automatic variables. Takemichi Mikey-kun. In a high level language, storage space for a variable can be allocated in one of the three ways: statically, dynamically, automatically. Statically, variables can be allocated in the .data, .read data, RO data, or .bss section. The storage space is reserved and usually initialized when the program is loaded and begins execution. Right, so this I get, but what is the difference between this? No, .bss dot read only data and .data, initialized data dot read only data which cannot be changed, uninitialized. That makes sense. Initialized data, uninitialized data, and data that can only be read.